Hello Stage 1 chemistry students. We're having another attempt at a different location where I'm going to practice presenting to you so that you can't give me coronavirus, because I'll be at home and I'll be protected. I got a dog in the yard, so don't come near me with the coronavirus because the dog will get you. So I have a couple of pictures here that I've been instructed by my daughter, who was sick today, to not remove, so we're just going to leave that. We are concerned with this area here and this area here. Now, what we're concerned with is H+, i.e. acid. So the definition of an acid from the Bronsted-Lowry definition is anything which donates a proton, and a base is anything which accepts a proton. A proton is a hydrogen which has donated its electron, so it becomes H+. So here are the common acids that we see most of the time. Hydrochloric acid, sulfuric acid, nitric acid, phosphoric acid, and then carbonic acid and acetic acid. Now some of these you might already be a bit familiar with because you've been naming things like this, only you would have called it hydrogen chloride, hydrogen sulfate, hydrogen nitrate, hydrogen phosphate, hydrogen carbonate. Now when we're looking at this arrangement here, well, they actually have common names too. So that might be called acetic acid, but its common name is vinegar. So its common chemical name, which is not the common cooking name, is acetic acid. This is hydrochloric acid, sulfuric acid, nitric acid, phosphoric acid, and carbonic acid, and acetic acid. Those are the acids. Some are strong, others are weak, and we'll chat on that in a second. And then we've got three common bases. These, when I say they're common, they're ones you need to know for stage 2 chemistry. So you've got sodium hydroxide, sodium hydrogen carbonate, otherwise known as baking soda, and sodium carbonate. They are three very common bases that we tend to come across in stage 2 chemistry. Now when we look at any acid, what we've got to realise is that most of the time you don't have a proton just kicking around in water doing nothing. It's always going to get mopped up by something because it's a positive. So it's attracted to anything which is negative. And what we often find is that the H+, when it's dissolved in water, will find a water molecule and make this here, H3O+, which is what we call the hydronium ion. Now if you look at the water itself, remembering that it's got a bent shape due to VSEPR, valence shell electron pair repulsion theory, those two lone pairs push the protons down that it's bonded to covalently. Well, this acidic proton comes along and it pinches one of the lone pairs, and it'll quite happily sit there. But you see, the thing is that we represent this with what we call an equilibrium arrow, which can go forwards and backwards because it can go onto the lone pair and come off again. The difference is that these two protons here, these hydrogens, are covalently bonded with the oxygen. That's a permanent chemical bond. This, however, is an attraction. So it's not regarded as a permanent chemical bond, and hence this proton can come off and on again. And that's important because when you want to add an acid to any situation, you want the acid to be able to do its job. You don't want it to be permanently stuck to water, then you can't use the acid. You want the acid to do something, well, then it needs to be able to separate the proton off the hydronium ion and go do its job. Now we can see here ionization equations for several of the main acids. You can see if you add hydrochloric acid to water, it becomes H+, aqueous, and Cl-. This is what we call a monoprotic acid because it gives off one proton. Sulfuric acid is an example of a diprotic acid. When you mix it with water, it gives you two protons and the sulfate ion. Phosphoric is an example of a triprotic acid. When mixed with water, you get three protons and the phosphate ion. Your chloride, sulfate, and phosphate ions in these situations are, what's the word for it? Spectator ions. They don't actually participate in the reaction itself. Now these are referred to as strong acids because when you put them into water, they immediately kick off those protons. They dissociate immediately. And that means that all these H+ are floating around, attaching to water, ready to react as an acid. When you've got something like vinegar, for example, though, the same with carbonic acid, these are what we call a weak acid. So that means most of the time that acidic proton stays on the acid itself. It doesn't actually come off. So rarely will it go across to become a proton on this side and what we call the acetate ion. There should be a little aqueous there. I've missed that out. So The reason vinegar is okay to put on fish and chips and salt and vinegar chips and all that sort of stuff is because it's not a strong acid. It's an acid. I mean, if you get vinegar and you put chalk into it, it'll still react. I'll go do that a little bit later, make a point of it. But you can add this to your tongue and your tongue doesn't get a tremendous chemical burn. If you add this, or this to your tongue, you'll cause permanent damage, and I highly don't recommend it. I put this into my pool, and when I open the bottle, it's fuming, and you can't breathe it in because it sucks. It really hurts the lungs. So some of it splashed once, and it all landed on my legs, and my legs started bubbling along with the bricks that it fell on, and it hurt like, oh man, that was so painful. I had to run and get the water and wash it off as quickly as possible. Luckily I was close to the garden hose. This is why whenever we handle any of this stuff, and you will handle these two in concentrated form in stage 2, you do it with all the safety equipment and a safety shower and the eye wash station. It's part of the health and safety for chemistry. Now, so we've talked about here, these guys fully dissociate. This will only partially dissociate, so a lot of it still sits as this acid, and that's why chemically it's not that active, but it will still dissolve stuff. Sodium hydroxide plus water gives you sodium, and this what's the hydroxide ion here. This is a strong base. Sodium hydroxide is basically Drano. When you have a drain plugged up with all the hair and fat and other garbage that goes into drains from human bodies, and you need to unplug that, this is what you use. Drano goes in there, it dissolves all the, well, it doesn't dissolve, but it reacts with all the fats, breaks them down, and then the drain clears. This stuff here, if you get it on you, you'll get a nasty chemical burn. It's really powerful stuff. You need to stay away from it. Other ones, such as baking soda, well, that's perfectly fine. That's what we put into our sherbet. We had that and citric acid, and you know, bubbles on your tongue. This stuff's not that great either. Like sodium carbonate is not as bad as sodium hydroxide, but it's still reasonably reactive, so you got to be careful with it. When you do have a hydroxide, especially something like sodium hydroxide, which dissociates fully into water as Na and OH, the hydroxides will fly around, and they will fly around as a polyatomic ion, and if they come into contact with an acidic proton, they will form water, because OH minus plus H plus makes H2O, and this is what we call the neutralization reaction. So if you've got a really acidic environment, you can add hydroxide and it will reduce the acidity, because of course the more H plus you have, the more the acidic environment there is. Okay, hope that was useful. The whole point of this is to make you understand where the whole H plus comes from when it comes to solving reduction and oxidation reactions in an acidic environment. Thank you. Good evening.